The topic of waves often confuses students. Concepts like wave interference, phase difference, and path difference make it difficult to conceptualize the double slit and diffraction grating experiments. In this video, we will build the theory of waves from the ground up. We can begin with a circle and imagine moving a point around its circumference. If we track the vertical height of that point over time, we see a wave begin to form. The maximum height the point reaches is the amplitude, and the length of one complete cycle is the wavelength. In general, the wavelength is the distance between two consecutive points that are in phase. When two waves travel in the same direction, their amplitudes add. This is known as the principle of superposition. If the waves are aligned, the result is a larger wave. This is called constructive interference. If the waves are opposites, their amplitudes cancel, resulting in no wave. This is known as destructive interference. These ideas form the foundation of Fourier analysis, which tells us that any complex wave can be broken down into simpler sine and cosine waves. Because waves are cyclical, we can represent the phase of a point using a rotating arrow. For a traveling wave, the phase at the end point is especially important. Let's consider some key phases. Using these, we can relate phase difference to path difference. Comparing the orange and green point, the phase difference is pi over 2 radians, and the path difference is a quarter of the wavelength. Comparing orange and blue, the phase difference is pi radians, and the path difference is half a wavelength. Comparing orange and red, the phase difference is 1.5 pi, and the path difference is 3/4 of a wavelength. Comparing two orange points, the phase difference is 2 pi, and the path difference is exactly 1 wavelength. This final case shows that after traveling a full wavelength, the wave repeats. The points are in phase. Understanding the phase of a wave allows us to determine whether two waves are aligned or opposite. Currently, the waves are the same because they are in phase. However, if the orange wave shifts by half a wavelength, it becomes out of phase. If these two waves then meet, they cancel out. We can think of a wave as a traveling phase arrow. As it progresses, its phase changes. The path difference is the extra distance a wave travels, which leads to a phase difference between the waves. Here are some important relations between phase difference and path difference. A path difference of half a wavelength corresponds to a phase difference of pi. A path difference of 1 full wavelength corresponds to a phase difference of 2 pi. This shows that waves will be in phase again for every multiple of the wavelength. In the double slit experiment, we use a coherent light source, meaning it has a single frequency and a constant phase difference. If we take a wave front and use it to form a second source, we see the familiar pattern of wave interference. The resulting pattern is a series of maxima and minima. But what's actually happening? We can track the paths taken by waves from the first and second sources. By comparing these paths, we can draw a simpler diagram to visualize what's going on. At the center of the screen, both waves travel the same distance. They are in phase, creating a central maximum. As we move to the next maximum, the waves must be in phase again, otherwise they would cancel. Since they are in phase again, the path difference must be 1 wavelength. In fact, At any maximum, the path difference will always be a whole number multiple of the wavelength. Let's focus on the triangle formed by the path difference. We label the slit separation as S, the distance between the slits and the screen as D, and the fringe width as W. This creates another triangle we can analyze. To make progress, we make some reasonable assumptions. In practice, both wavelength and fringe width are very small, especially when working with light. We assume the triangles are approximately isosceles, allowing us to complete the missing sides. We assume the triangles are nearly right-angled, and we assume the triangles are similar. Using these assumptions, we can write expressions for the angle in two different ways and equate them. This gives us the key relationship. W over D is equal to lambda over S. Looking back at our diagram, we can now predict what happens when we change each variable. For example, if lambda increases, W also increases. This formula neatly captures the relationship between fringe width, distance to screen, slit separation, and wavelength. A diffraction grating is essentially a double slit with more slits. We still observe an interference pattern, and the waves behave in the same way. At the nth maximum, the path difference is n times the wavelength. The slit separation is now labeled D. Again, we see a triangle, which we can approximate as a right-angled triangle. This lets us write an expression for the sign of the diffraction angle. From this, we can derive the standard equation used in diffraction grating calculations. Thank you for watching. If this video helped you understand waves more clearly, please consider liking and sharing it. And if you'd like to see more content like this, don't forget to subscribe and turn on notifications so you never miss a future upload.